welcome everyone. The side session, although it's quite full, so nice to see you. The first presentation is going to be about, harnessing wave intrinsics. Something that I struggle with a lot too. Often turns and stabs you in the back, I found out. Looks better, but not always. So yeah, I'll leave you the stage and good luck.
Great. Well. Hi, it's nice to meet you. I'm Alex. It's nice to be presenting to all of you. The last time I practiced, it was to my cats. So people is a bit more fun. They're not the chillest cats either. Yeah, I'm Alex. I'm one of the 6 Alexes at Snowden Studios. Snowden Studios is a work-for-hire company based out of Ottawa, Ontario, Canada. We worked on a variety of projects from indie to AAA. And today, I was hoping to talk to you a little bit about wave intrinsics. I think wave intrinsics are a really neat way to share across your threads in a wave on your GPU, and I just think they can enable some really interesting and powerful algorithms. So out of this talk, I'm hoping you're going to gain an intuition for how wave intrinsics are implemented, as well as when you want to use them. To do that, we're going to look at a common and a novel use case for wave intrinsics that hopefully will give you some inspiration for creating your own algorithms. But first, I want us to meet our imaginary GPU we're going to be using today. It's a simple GPU, 4 lanes. Unlike a regular GPU that would maybe have 32 or 64 lanes, it's pretty much can do everything else though. It has independent processing of your data streams, and again, does everything else a regular GPU does, except it lives in my imagination, and now hopefully in yours. But now that we have independent streams of information. What if we want to share across those lanes? Maybe our lanes are feeling lonely, they want a little bit of companionship. Maybe each of our lanes, we want to take the output of all of our lanes and output them to a single value. You could use an atomic add to device memory or something like that, but there's a better way to do that using wave intrinsics. One way we could do it would be by iterating through each of our elements in lane 0. So lane 0 would read the value of lane 1, add it to its output, and then lane 2, and then lane 3. So on and so forth. The challenge with that is that it doesn't scale particularly well. If you have a wave size of, say, 32, then you're doing 31 iterations. But thankfully, there's a better way to do that. Let's say, instead, let's start over. We have our results. And we want part of our lanes to participate in our summation. So lane 0 will read from lane 1 and add it to an intermediate result. And then lane 2 will read from lane 3 and add that to its own intermediate result. And then we have an additional step where we double the distance to the next result. So lane 0 now reads from lane 2. If we were to follow the lines of data, we can see that lane 0 ends up reading all of the values of all of our lanes. And we've essentially summed up all of the values within our wave. Keep in mind that as we double the size of our wave, let's say we had 8 lanes, then we would double the distance again. We would go from a stride of 2 to a stride of 4 for the next step. And then for a wave size of 16, we would have a stride of 8. We've turned our problem from a linear solution into a logarithmic one, which scales particularly well. In this case, we save 1 iteration. But in the case of a wave size 32, we save 26 because we would have done 31 linear iterations with the lane 0 version. In HLSL, you've probably used this through the wave active sum intrinsic. It doesn't have to be implemented this way, but for the convenience of this presentation, we'll go into a bit more detail on why this version is the one we're using right now. So let's look at a common example used in many games. You've probably, if you've done any GPU-driven rendering, have used this. It's called stream compaction. And so let's say I have 4 letters. And for some reason, I've decided that I want to output my favorite letters to a buffer. In this case, I've decided that A, B, and D are my favorite letters, not C. So our output buffer would look something like this. No C, and we want to do that efficiently. One way we could do that would be by setting a value of 1 and a value of 0 for each lane that we want to output to our output buffer. In this case, A, B, and D are my favorite letters, so they get a value of 1. What we do is we use the same thing that we did for wave active sum. We read our direct neighbors. In this case, we're going from right to left instead of left to right. And then again, you double the distance. Each time we read outside of our wave, we just read a value of 0. We just add nothing to our result. And you see that as we reach the end of this graph, this diagram, each value is simply the sum of all of its preceding neighbors, including itself. This would be known as an inclusive prefix sum. And in HLSL, you might use, oh, we'll get back to that. So now that we have these values, we can subtract 1 from them and know where we want to output in our buffer. You can see here on lane 3, we know that by subtracting 1, 2 of our previous neighbors would want to write to our output buffer, so we know we want to write to index 2. Lane 2 here doesn't write anywhere because it's not a favorite letter. We don't care about it. In HLSL, this formulation would be a wave prefix sum, except for the fact that, like I mentioned, this formulation is the inclusive prefix sum. The exclusive prefix sum would simply not include our current lane's values, so lane 3 would have the value of 2 in this case, and that would be the result of wave prefix sum, which is very effective when you're looking to do things like culling. Maybe you have a bunch of lights you're looking to cull, and you're trying to do some frustum culling on your GPU, and then you want to output all the lights that you want to use in your lighting shader through some mechanism. And what you do is you tag all the lights that you would call, and then use stream compaction to pack them into a single buffer you can use in your lighting shader. A lot of these intrinsics are already built for you, as I've previously shown. Wave active sum and wave prefix sum. In GL land, you would probably call it subgroup add or subgroup exclusive add. And there's some great resources for that over on the DirectX wiki or the Chronos subgroup tutorial. I highly recommend taking a look at both of those. Something that I think is important is for us to identify and learn how wave intrinsics compile. Knowing how they compile will give you some valuable insights into the potential performance characteristics of your algorithms. You can know what the compiler engineers have decided to turn your wave intrinsic into. So let's look at a simple program. This is pretty much the program we just discussed. We take some input, we select whether we want to write it out to our output buffer or not, and then we use wave prefix sum to determine the output index in our output buffer. I'll take you a moment to read that. If we look at the disassembly for wave prefix sum, oh, I forgot to mention, we're using AMD's offline compiler, AMD LLPC for the disassembly here. And if we look at the disassembly for wave prefix sum, it's a fair bit of instructions. Unfortunately, it's not as simple as read your neighbor's value. There's some work here to shuffle your neighbors around to do the exclusive sum, and there's some intricacies here with how we do the additions that I would love to talk to someone who's implemented this so they could tell me why it's done this particular way. But I did lie. We don't have to use wave prefix sum in this case. We can use the much simpler wave prefix count bits. The challenge with wave prefix sum is that it's a general function, right? We can add arbitrary integers or floating point numbers. Wave prefix count bits is simply for 0 and 1. We can use much quicker binary operations. So instead of wave prefix sum, we would use wave prefix count bit on our bool result. On AMD's offline compiler, this compiles to 2 instructions instead, which is likely probably better than 40 instructions. But now that we've talked about stream compaction, I thought I would talk a little bit more about an algorithm we use on a project currently in production. It's something I like to call wave-wide interpolation. Let's say you have 4 spheres, and then you have a point that wants to interpolate the color of each of those spheres. So each sphere has a radius, it has a color, and this point wants to combine the results of all of those spheres based on a series of recursive linear interpolations. And so in this case, maybe the blue sphere has a higher priority than all the other spheres, so that should be the last one in our interpolation. I swear there was a real use case for this. It's not completely arbitrary. What this would look like could be a little bit something like this, where we have one sphere that I hope you can yeah, you can't see that. There's a sphere here, I promise. And each point, as they enter the sphere, are gaining the color of the sphere, and as they exit the sphere, they lose the color. Yeah, I swear, like you can kind of see the Fresnel on it somewhere, but that's okay. But let's say, instead of having a few spheres and a few points, we have a ton of spheres and a ton of points. Maybe they're spawned by some dynamic GPU compute algorithm. If we explore the parallelism inherent in our problem, the efficiency of our problem depends on the number of points and spheres we're processing. If we're processing 1,000,000 points, we can just spawn one thread and then loop through all of our spheres. Let's say we have 4 spheres in this case, so we have one thread per point, and we just iterate 4 times in each sphere for each sphere. Great. But what if we have 128 points and 128 spheres? Now we're looking to spawn 128 threads, and they're looking to iterate 128 times, which is not the best use of our GPU, especially as the number of spheres grows. Maybe we have 1 point and then 1,024 spheres. Now we have one thread processing 1,024 spheres in in a loop. Not ideal. Especially if we look at an example RDNA GPU with 26 work group processors that can spawn up to 66,000 threads. 128 threads is a mere 0.1% of your GPU's potential capacity, so it's not necessarily the best use of our GPU here. Thankfully, we can do better than that. We can spawn a thread per point sphere pair. And if we were able to do that, we would be able to spawn 16,000 threads instead of 128 threads, and then each thread does a little bit of work instead of a lot of work. We'll go into a bit more detail on how we could implement that. First, I think it's important for us to look at the algorithm that I've just described. Here, as you can see, we're iterating through each point, and then for each point, we iterate through each sphere, calculate its influence, and then we do a linear interpolation based on our sphere's influence. You can see here that we have a loop dependency with our color value as we continue to process it at each iteration. In our first solution, we were spawning one thread per point. You could think of that even on the CPU as just a parallel 4 or something like that. What I'm pitching is that instead you spawn a thread group per point and then a thread per sphere. But the issue is that loop dependency I just described, where our value color here depends on the results of our previous iterations. Thankfully, if we look at the algebra, we'll be able to break that down and actually implement a version that more effectively scales across our GPU. So let's look at our small 4-lane GPU again. It has 4 letters, A, B, C, and D, and for some reason I want to interpolate all of those letters. I don't know what the interpolation between A, B, and D is, but for this particular case, you can imagine it. I've also set lane 0's interpolation term here to 1, just to simplify the algebra. So in practice, what we're looking to calculate is something a little bit like the equation here, which is just a bunch of recursive lerps. If we break down the algebra, and we actually just break down our lerp and we look at each iteration, you might be able to start noticing a pattern. Lane A here is actually looking to read the results of lane 1, 2, and 3. B here is looking to read the results of lane 2 and 3. Lane 2 here with C is looking to read the value of lane 3. And, and D here doesn't want any friends. It's just alone in its own corner. And you might be thinking, that looks a lot like a wave prefix operation, just in the reverse order. So for the simplicity here, what we can do is we can take our values and just reverse the order. And now, as you can see here, A here, lane 3, reads the results of lane 2, 1, and 0. B reads lane 1 and 0, so on and so forth. You can imagine that this is just the algorithm we looked at previously with the wave prefix sum, except with multiplication this time. So that's what we do. We use the HLSL Intrinsics wave prefix product, and then we combine the results with a wave active sum. And with that, you get this function. With this, we were able to take a problem that might be difficult to scale well on our GPU and turn it into something that can more effectively make use of our GPU's cores. If we look at a simple simulation here, I've simulated 1,024 spheres being influenced by 1,024 points. You really can't see the spheres here, but you know, imagine them. They look great on my screen. But yeah, on my Intel iGPU, this goes from 0.6 milliseconds on the naive solution to 0.3 for the fully parallelized version. And then 0.4 on my RTX 3070 Ti to 0.1. I would like to point out a word of warning, though, before you go on with this. The code generation for Wave Intrinsics cannot be as optimal as you might think. And again, depends on your compiler. In this case, we're using AMD's offline compiler. But if you use wave read lane at, in this case, if you were to use it to shuffle, you end up with a waterfall loop. And I'll go into details on what a waterfall loop is in a second. But in this case, what we're trying to do is we're trying to read our current wave's index plus 1. So we're trying to read the value of our neighbor to our right. And we're trying to shuffle the results of all of our lanes such that we just rotate them to the left. And maybe we want to use the more constrained spur V shuffle up instruction intrinsic, although that's the reverse order from the wave read lane I just described. That's OK. We still end up with a waterfall loop. But I haven't really described what a waterfall loop was. So let's go over that. A waterfall loop is pretty simple. It's essentially a way for us to iterate through each unique value in our wave. In this case, we start with an infinite loop where each lane is active, and we read the first active lane. Let's say our wave has the values A, B, and D. So our first active lane has the value of A. Each lane that matches the value A enters the branch, does some work, and then breaks out. That means each lane that had that same value is now inactive. And then maybe the value B is the next one we read. Each lane that matches B goes into the branch, does some work, and then breaks out. And slowly, what we're doing is we're going through each lane, making them inactive as we process the unique elements in our wave. Which is great when maybe we only have one unique value in our wave, then we only do one iteration. But in the worst case, we iterate the number of lanes in our wave. So on an AMD or an NVIDIA card, maybe you do 32 or 64 iterations. There's some other utilities to waterfall loops than just that, but in this particular case, where we're trying to do a wave read lane at, where each index is going to be different, we're going to be doing an iteration per lane in our wave, which is not ideal, especially when, in some cases where we saw with the wave active sum, the compiler was able to generate a much more optimal sequence of instructions. If you think of your GPU as a lens you can use to navigate your problem space is to think of your GPU as a superpowered loop unrolling machine. Like we saw with the wave active lerp, when we were showing the two loops with the points, the left version, the fully serial version here, would be the one we run on the CPU, where one thread loops through each point, then loops through each spheres, and we do sphere points times point count number of iterations. And on the far right, we have the final version we came up with, which is the fully parallel version, where we have one thread per unrolled loop iteration. What I find interesting here is you can pick the point in your algorithm, the way you want to structure your algorithm to pick a point in this gradient. You're not stuck to picking fully parallel or fully serial. Maybe one thread iterates through 8 spheres, and then all of those threads combine their results. Or maybe you pick, 16 spheres. You can really balance it based on the data and the parallelism inherent in your data. Here are some spaces you can look at to develop your own algorithms. Particularly, I suggest exploring the literature. A lot of these algorithms go back to the 70s, and they're just really interesting. If ever you want to chat, you can find me on Mastodon. I'm not super active, but feel free to take a look there, as well as my blog whenever I post, which is somewhat rarely. And then here are some references. These are really excellent. I recommend you take a look at all of these and more if you find them. I'd like to thank you all for your time. If you have feedback for me, if you have questions or discussion, please reach out to me after this talk. Any questions? Yes, sorry. It was recommended to me I make a QR code for all of it at once, but I couldn't figure it out. No problem. Yeah, right? I just wish there was like a website I could be like, give me these links, please, all in one QR code.
Actually, I want to ask something. It might be outside the talk or not, but how similar is it in hardware to the whole like reduction sum, where it does for example, for the wave active sum? Do you know if in hardware the sum is somehow take 32 and add them together, or do they do the reduction, sort of the log2 reduction that you were showing when I call wave active?
In hardware?
Yeah, as in, we obviously one instruction on the, I guess.
Oh, the wave active sum wasn't one instruction. It ends up being like.
Oh, sorry, the count bits one, I guess. Yeah.
The count bits one, yeah, the count bits one on hardware, and I'm not an AMD like developer, so please, if someone knows better, please answer for me. But it's because a lot of your the ISA for our DNA has built-in support for a lot of these bitwise operations based on your lanes, because that's how maybe you would do like your execution masks and all that stuff. So that's already built in with the hardware. So it's already like a bit mask, and then you just, once you have your execution bit mask or something like that, you just take your lane index, you create a mask based on that, and you just AND that. So in theory, it's very simple to implement. You could even do it yourself in a few instructions if you just had access to the execution mask. If that helps.
Yeah, that's the
Okay.
if there's any special hardware, or if it's just...
If there's special hardware, I don't know.
access to the register.
Yeah, right. Yeah.
It depends. So that's the default answer, but it really depends on the GPU we're working with.
Right.
So you can't like assume anything unless you work for consoles.
Right.
For consoles, you can kindly ask your console
My happy
provider
place.
and ask them how it's implemented. But it really depends. But if there's instruction code, it's possible it's implemented in hardware, of course. And it could also be something that the firmware does.
Okay, thank you.
Cool.
But normally, if there's an instruction code in the white paper, then there's probably hardware for it, but it's not guaranteed.
Interesting. Thank you.
Thank you.
Any other questions?
Yeah, it was quite surprising that this wave prefix sum ends up in this giant
Yeah.
assembly code. Was it in your experience and also like significantly slower compared to the count bits?
I'm not gonna lie to you. I didn't measure, so I don't know by how much slower it is. There are some considerations on AMD hardware, and again, not an AMD hardware engineer, so take it with a massive grain of salt. But the distance you take when you do your strides across your lanes has a performance impact. At least that's what I found in some of the references. So the wave prefix count bits doesn't need to do that stride. Across, like, I think there was something where like across 8 lanes it gets more expensive, across 16 it gets more expensive, and I think across 32 it drops off a cliff or something. I'm getting some nods, so I'll take that as potentially correct. Yeah.
Do you maybe have some experience with using wave intrinsics that sound great at first and in the end are such a performance?
Yes, but not for this particular case. I think I had some notes about that I forgot to bring up, but wave intrinsics are not, like, they're not always the best tool. Like if I'm processing a stream of information, a wave intrinsics to sum up 32 numbers takes 5 operations. But if I want each lane to just process its own information, I can do 32 elements in 1 operation. So doing the wave intrinsics is a great way to maybe collect the results at the end, but not necessarily the best way to do all of your work. Yeah.
So, is it stuff that you do only in uniform control flow, or is there a pattern to dealing with non-uniform control flow?
It depends, but yeah, like some of this code will just handle it. Like I don't have this offhand, so it's something you can find in the spec generally. But like wave active sum in the name considers it like wave active sum, so each inactive sum I think will just add 0 instead. So considering your active lanes is something you have to keep in mind when you're working with wave intrinsics. You also have to keep in mind like helper lanes and a bunch of other things you have to consider, unfortunately. We can't just be clever and not have to worry about it afterwards. Or you could just use atomics. And I have a whole set of slides I had to cut about optimizing atomics that I just couldn't fit in this slide. So maybe I'll have a blog post about that. Turns out fitting stuff in 20 minutes is kind of tricky. Cool. Thank you all.